Saturn's rings are dying. Right now, as you read these words, thousands of tons of ancient ice are raining down onto the planet below, pulled by gravity in a slow, inexorable spiral. In just 100 million years, maybe less, those magnificent rings, the signature feature that makes Saturn unmistakable in any telescope, will be gone, vanished, as if they never existed. And here's what will astound you. They may have appeared around the same time dinosaurs walked the Earth. The rings you see through a backyard telescope tonight aren't ancient. They're recent, temporary. A cosmic accident we're extraordinarily lucky to witness. If you had lived 100 million years ago and somehow looked up at the sky, Saturn might have been ringless, just another gas giant hanging in the void. But the mystery doesn't end there. Right now, as you sit still, you are hurtling through space at over 800,000 kilometers per hour. Not falling, not drifting. Racing. The Earth spins beneath your feet at more than 1,600 kilometers per hour at the equator. It orbits the Sun at 107,000 kilometers per hour. The Sun itself, carrying our entire solar system with it, barrels through the Milky Way at 828,000 kilometers per hour. And yet, you feel none of it. You sit perfectly still, breathing calmly, as if suspended in absolute stillness while the cosmos wheels around you in vast, silent arcs. This is the first mystery of our solar system. Not its size, though it stretches beyond imagination. Not its age, though it has endured for 4.5 billion years. The first mystery is how something so dynamic, so filled with motion and violence and change, can feel so peaceful. How worlds carved from catastrophe can hold such quiet beauty. How orbits traced by gravity's patient hand can appear as fixed as clockwork, even as everything shifts and evolves across deep time. Our solar system is not what we once imagined. It is stranger, more intricate, more alive with hidden drama than the simple diagrams we drew as children might suggest. There are moons with subsurface oceans warmed by tidal squeezing, planets where it rains diamonds, asteroids older than mountains, untouched since the solar system's birth, ice that remembers the earliest moments of planetary formation. And at the center of it all, a star that will one day swell and consume the very planets it brought into being. But tonight, something is different. Tonight, we have new answers. In just the past few years, spacecraft have flown closer to the Sun than ever before, surviving temperatures that would melt steel. Probes have dived between Saturn and its rings, measuring their hidden secrets. Rovers on Mars have discovered wave-rippled rocks that could only have formed in shallow lakes open to an atmosphere. And high in the sulfuric acid clouds of Venus, scientists have found that the building blocks of life, amino acids and nucleic acid bases, can survive for weeks, perhaps longer. The solar system is revealing itself to us, layer by layer, secret by secret. And some of what it's showing us changes everything we thought we knew. Tonight, we're going to drift through this cosmic neighborhood. Not as tourists, but as residents trying to see our home with fresh eyes. We'll travel from the Sun's blazing corona, just measured by a spacecraft that passed within 6.1 million kilometers of the surface and survived, to the frozen darkness beyond Neptune, where a hidden ninth planet might still be lurking. We'll visit worlds of sulfuric acid that might harbor life, and worlds of methane rain where you could fly with wings attached to your arms. We'll trace the invisible threads that bind moons to planets and planets to the Sun. And we'll discover that even in our own backyard, the universe holds secrets we're only beginning to understand. So settle in. Let your thoughts slow like settling dust. Let your breath find its rhythm. Because in the quiet that follows, there are 100 wonders waiting to be whispered, one by one, like secrets shared between old friends beneath a sky full of stars. Hello there, and welcome to Sleepable Science. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're simply the kind of person who finds peace in pondering the vastness beyond our small blue world. Either way, this journey is for you. You have nothing to do but rest. Let your mind relax, your muscles soften, and your breathing deepen. Let go of the weight of the day. Tonight, we're staying close to home, cosmically speaking. We're exploring the solar system, that small corner of the Milky Way where Earth makes its quiet orbit. 8 planets, countless moons, rings of ice and rock, and a star at the center of it all. This is where we live. This is where life, as far as we know, first opened its eyes and looked up at the sky. Some of what you'll hear tonight may surprise you. Recent spacecraft have revealed worlds more complex than we imagined. Missions to distant moons have found evidence of hidden oceans. Probes have touched the sun's atmosphere and survived. Rovers have discovered hints that Mars once had rivers and perhaps even rain. The solar system is not a museum of dead rocks frozen in time. It's a living, changing, breathing system still writing its story. If these quiet explorations help you unwind, if they give you a peaceful way to close your eyes and drift, consider liking and subscribing to the channel. It helps others find their way here too, one curious soul at a time. Now, let your eyelids grow heavy. Let the stars come out in your mind's eye. And let's begin this slow, soothing journey through the 100 facts about our solar system. The Sun, our central star. The Sun is not a ball of fire. This is perhaps the most common misunderstanding about the star at the center of our solar system. Fire requires oxygen, a chemical reaction between fuel and atmosphere, and the Sun has neither. What powers the Sun is something far more profound, something that happens only in the hearts of stars. Deep within its core, at temperatures reaching 15 million degrees Celsius, hydrogen atoms are crushed together with such immense force that they overcome their natural repulsion and fuse into helium. This process, called nuclear fusion, converts mass directly into energy according to Einstein's famous equation, E equals mc squared. Every single second, the Sun transforms 600 million tons of hydrogen into helium, and in doing so, loses 4 million tons of mass, converted purely into energy that radiates outward in all directions. That energy has traveled 150 million kilometers across the vast emptiness of space to warm your skin right now. The Sun contains 99.86% of all the mass in the solar system. To put this in perspective, Jupiter, the largest planet, is barely 1,000th of the Sun's mass. All the planets combined, all the moons, asteroids, comets, rings, and dust, every solid object we've ever discovered orbiting our star, make up only a tiny fraction of what remains. The Sun is so massive that its gravity holds every world in the solar system in orbit, from Mercury, which circles at breakneck speed just 58 million kilometers away, to distant Neptune, nearly 30 times farther from the Sun than Earth, still bound by invisible threads of gravitational force. Even the objects in the Oort cloud, trillions of comets drifting in the cold outer reaches tens of thousands of times farther than Earth, remain tethered to the Sun. The Sun's mass is about 330,000 times that of Earth. If you could place it on a cosmic scale, one side would need 330,000 Earths to balance. Yet for all this mass, the Sun is surprisingly empty compared to solid objects. Its outer layers are less dense than Earth's atmosphere at sea level. If you could somehow stand on the Sun's surface, which you cannot because there is no solid surface to stand on, you would sink through layers of hot plasma like a stone dropping through fog. Only as you descended toward the core would the density increase dramatically, compressed by the crushing weight of all the material above. At the very center, the core is about 150 times denser than water. a seething, pressurized furnace where matter behaves in ways we can barely comprehend. The visible surface of the sun, called the photosphere, is where light escapes into space. It appears solid from a distance, a golden sphere hanging in the sky, but up close, it reveals itself as a turbulent, ever-changing landscape of plasma. Vast convection cells, each larger than the state of Texas, rise from below, carrying heat from the interior. These cells, called granules, release their energy at the surface, cool, and sink back down in a continuous cycle. The sun's surface has a mottled, grainy appearance because of these granules, like a pot of boiling water frozen in time. Sunspots are dark patches that appear and disappear on the sun's surface over days or weeks. They look dark only because they're slightly cooler than their surroundings, about 3,800 degrees Celsius compared to the photosphere's 5,500 degrees. These spots mark regions where powerful magnetic fields erupt through the surface, temporarily inhibiting convection and cooling the plasma. Some sunspots are small, barely larger than Earth. Others are enormous, spanning tens of thousands of kilometers, large enough to swallow multiple Earths whole. Sunspots often occur in pairs or groups, and they tend to cluster near the sun's equator during solar maximum. The sun has an atmosphere, though not one you could breathe. Just above the photosphere lies the chromosphere, a thin layer of hot gas about 2,000 kilometers deep. During a total solar eclipse, when the moon blocks the bright photosphere, the chromosphere becomes visible as a reddish ring around the sun's edge, its color coming from hydrogen atoms emitting light at specific wavelengths. Above the chromosphere stretches the corona, a ghostly halo of superheated plasma that extends millions of kilometers into space. The corona is one of the great mysteries of solar physics. The photosphere is a mere 5,500 degrees Celsius, but the corona reaches temperatures of over 2 million degrees, sometimes spiking to 10 million degrees or more. Somehow, energy is transported upward from the denser layers below, heating the tenuous corona to temperatures 200 times greater than the surface. Scientists are still debating exactly how this happens. Some energy may be carried by magnetic field lines that thread through the corona, heating the plasma when they reconnect. Other energy may come from sound waves generated by convection in the photosphere, which steepen into shock waves as they rise through the less dense atmosphere. Recent observations from the Parker Solar Probe suggest that small-scale eruptions called nanoflares, thousands of tiny explosions occurring constantly across the sun's surface, might collectively heat the corona. The corona extends millions of kilometers into space, gradually thinning until it becomes the solar wind. This wind is not made of air, but of charged particles, primarily electrons and protons, streaming outward from the sun at speeds ranging from 300 to 800 kilometers per second. Near Earth, the solar wind has a density of about 5 particles per cubic centimeter, far more tenuous than the best vacuum we can create in laboratories. Yet it fills the entire solar system, creating a bubble called the heliosphere that shields us from interstellar radiation. The solar wind pushes against planetary magnetic fields, compressing them on the sun-facing side and stretching them into long tails on the night side. It shapes the tails of comets, always pointing away from the sun, regardless of the comet's direction of motion. And when it interacts with Earth's magnetic field, it creates the beautiful auroras that dance across polar skies. In late 2024, NASA's Parker Solar Probe made history by flying closer to the sun than any spacecraft ever had before. It plunged through the corona itself, passing just 6.1 million kilometers from the solar surface, close enough to touch the sun's outermost atmosphere. At that distance, the spacecraft experienced temperatures reaching over 1 million degrees Celsius, yet it survived, protected by a special carbon composite heat shield, 11.5 centimeters thick. Behind this shield, the instruments remained at a comfortable room temperature while gathering data from one of the most hostile environments in the solar system. The data Parker sent back revealed intricate structures in the solar wind, It detected switchbacks, abrupt reversals in the magnetic field direction that occur when field lines fold back on themselves. It measured coronal holes, regions where the magnetic field opens up into space, allowing plasma to stream outward at high speeds. It watched as magnetic field lines twisted, tangled, and reconnected, releasing bursts of energy. Every observation brought scientists closer to understanding how the sun's magnetic field shapes its atmosphere and drives the solar wind. The sun rotates, but not like a solid object. Because it's made of plasma, with no rigid surface, different parts rotate at different speeds. This phenomenon is called differential rotation. The equator completes one rotation in about 25 Earth days, while regions near the poles take over 30 days. Latitude 45 degrees north and south rotate in about 27.5 days. This variation is gradual, creating shearing forces that stretch and tangle the sun's magnetic field lines like rubber bands being wound tighter and tighter over time. Eventually, these tangled magnetic fields become unstable. They snap and reconnect, releasing enormous bursts of energy in events called solar flares. The largest flares can release as much energy as 10 billion 1 megaton nuclear bombs exploding simultaneously. They emit radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. Coronal mass ejections often accompany large flares, hurling billions of tons of plasma into space at speeds of up to 3,000 kilometers per second. These eruptions can have profound effects on Earth. When a coronal mass ejection strikes our planet, it compresses Earth's magnetic field, creating a shock wave that propagates through the magnetosphere. Charged particles funnel along magnetic field lines toward the poles, where they collide with oxygen and nitrogen atoms in the upper atmosphere, exciting them to emit light. The result is an aurora, curtains of green, red, purple, or blue light that shimmer and dance across the night sky. During particularly intense solar storms, auroras can be visible at much lower latitudes than usual. In 1859, during the most powerful solar storm ever recorded, auroras were seen as far south as the Caribbean. But solar storms can also cause damage. They induce electrical currents in power grids, sometimes strong enough to burn out transformers and cause widespread blackouts. They interfere with satellite communications and navigation systems. They increase drag on satellites in low Earth orbit, shortening their lifetimes. Astronauts in space are exposed to higher levels of radiation during solar storms, limiting their activities and requiring them to shelter in more protected areas of their spacecraft. The sun has a heartbeat of sorts, an 11-year cycle of activity driven by the periodic reversal of its magnetic field. At solar minimum, the sun's magnetic field is relatively orderly, and the surface appears calm, with few sunspots and minimal flare activity. As the cycle progresses towards solar maximum, the magnetic field becomes more tangled and complex. Sunspots proliferate, clustering near the equator. Solar flares and coronal mass ejections become more frequent and intense. At solar maximum, the magnetic field reverses, with the north and south magnetic poles swapping places. Then the cycle begins anew, with the field gradually simplifying as the sun moves back toward minimum. We are currently in solar cycle 25, which began in December 2019 and is expected to reach its maximum sometime in 2025. Early predictions suggested this would be a relatively weak cycle, but recent observations indicate it may be more active than initially thought, with sunspot numbers already exceeding predictions. The sun is middle-aged. It formed about 4.6 billion years ago from a collapsing region within a giant molecular cloud, a vast nebula of gas and dust drifting through the Milky Way. As the cloud collapsed under its own gravity, it began to spin faster, flattening into a disk. Most of the mass fell toward the center, accumulating into a growing protostar. The temperature and pressure at the core increased steadily as material piled on, and eventually, When the core temperature reached about 10 million degrees Celsius, hydrogen fusion ignited. The sun was born. It has been burning steadily ever since, converting hydrogen into helium at a rate of 600 million tons per second. This may sound like a lot, but the sun contains enough hydrogen to sustain this process for another 5 billion years. As hydrogen fuses, the helium ash sinks toward the core, gradually changing the sun's internal structure. Over billions of years, this has caused the sun to grow gradually brighter. When it first ignited, the sun was only about 70% as luminous as it is today. It will continue to brighten slowly over the coming eons. But the sun will not burn forever. In about 5 billion years, the hydrogen in its core will be exhausted. At that point, the core will contract and heat up, while the outer layers expand outward. The sun will swell into a red giant, growing large enough to engulf Mercury and Venus. Whether it will swallow Earth is uncertain. It depends on how much mass the sun loses during its expansion. Even if Earth survives, it will be rendered uninhabitable, baked by the intense heat from the bloated star looming overhead. During the red giant phase, the sun will begin fusing helium into heavier elements like carbon and oxygen. This phase will last for about 1 billion years before the sun exhausts its helium fuel as well. Then, unable to sustain fusion, the outer layers will drift away into space, forming a glowing shell of gas called a planetary nebula. What remains will be a small, dense white dwarf, about the size of Earth but with a mass comparable to the sun today. This white dwarf will be incredibly hot at first, over 100,000 degrees Celsius, but with no source of energy, it will gradually cool over trillions of years, fading slowly into darkness. For now, though, the sun remains stable, a cosmic furnace that has nurtured life on Earth for billions of years. Every photon of sunlight that warms your face, every ray that powers photosynthesis in a plant, began its journey at the sun's core. But the journey is not quick. Photons produced in the core don't travel straight to the surface. Instead, they bounce randomly through the dense interior, absorbed and re-emitted countless times. Each photon travels only a tiny distance before being absorbed again, gradually working its way outward through the layers of the sun. This random walk can take tens of thousands of years, sometimes up to 170,000 years, before a photon finally escapes from the photosphere and streams into space. From there, it takes just 8 minutes and 20 seconds to reach Earth. In that light is the energy of nuclear fusion, the power of stars delivered gently across the void. The sun is not still. It orbits the center of the Milky Way galaxy along with all its planets, moons, and smaller bodies, tracing a vast circle through space. This galactic orbit takes between 225 and 250 million years to complete, a period sometimes called a galactic year or cosmic year. Since the Sun formed 4.6 billion years ago, it has completed only about 20 galactic orbits. The last time the solar system was in this part of the galaxy, roughly 225 million years ago, dinosaurs were just beginning to emerge on Earth. The supercontinent Pangaea was still intact, and the Atlantic Ocean had not yet formed. The next time the solar system returns to this location, if anything recognizable as human civilization still exists, it will look up at a sky full of stars, many of them in different positions than the ones we see today, because the stars themselves are also moving, each tracing its own path through the galaxy. The sun also bobs up and down through the galactic plane as it orbits. It crosses through the plane about once every 30 million years, spending roughly half its time above and half below. Some scientists have speculated that these crossings might correlate with periods of increased comet bombardment or mass extinctions on Earth, though the evidence for such correlations remains inconclusive. The sun hums. Though space is a vacuum and sound cannot travel through it, the sun vibrates with millions of different sound waves trapped inside its interior. These are not sound waves in the traditional sense. They're pressure waves, rhythmic compressions, and rarefactions that propagate through the plasma. Each wave creates tiny oscillations on the sun's surface, rising and falling with periods ranging from minutes to hours. By carefully measuring these oscillations, a technique called helioseismology, scientists can peer inside the sun and map its internal structure, much like geologists use seismic waves from earthquakes to study Earth's interior. Helioseismology has revealed the thickness of the convection zone, the depth at which hydrogen fusion occurs, and the rotation rates of different layers inside the sun. The sun will outlive us all. Long after the last human has drawn their final breath, long after our cities have crumbled to dust and our monuments have been eroded to nothing, the sun will continue to shine. It is both our creator and, in a sense, our eventual destroyer. But for now, it is simply the star that makes life possible. The light at the center of our small cosmic island, burning patiently in the dark. It is the source of nearly all energy on Earth, powering the winds, the ocean currents, the water cycle, and the food chains that sustain life. It is the reason our planet is warm enough for liquid water to flow. It is the rhythm by which we measure our days, our seasons, our years. The sun is not eternal, but for now, it is constant. A golden sphere in the sky, 1.4 million kilometers across, 109 times the diameter of Earth. A furnace of hydrogen and helium, glowing softly across 150 million kilometers of space. A star among 200 billion others in the Milky Way, unremarkable in size or brightness, yet precious beyond measure, because it is ours. Mercury and Venus. The inner scorched worlds. Mercury is a world of extremes. During the day, temperatures on its surface can reach 430 degrees Celsius, hot enough to melt lead. At night, they plummet to minus 180 degrees Celsius, colder than the coldest place on Earth. This 600-degree temperature swing is the largest of any planet in the solar system, and it occurs because Mercury has almost no atmosphere to trap and redistribute heat. The planet is small, only slightly larger than Earth's moon, and orbits the sun once every 88 Earth days. But here's where things get strange. Mercury rotates on its axis very slowly, completing one rotation every 59 Earth days. This means that one Mercury day, from sunrise to sunrise, lasts 176 Earth days, or 2 full Mercury years. For an observer standing on Mercury's surface, the sun would creep slowly across the sky, hover near the horizon for weeks, and sometimes even appear to move backward due to Mercury's elliptical orbit. Mercury is the densest planet in the solar system relative to its size. Its core, made mostly of iron, accounts for about 85% of the planet's radius. This enormous core generates a weak magnetic field, surprising for such a small world. Scientists believe that Mercury's core is still partially molten, with liquid iron slowly solidifying over time. The surface of Mercury is heavily cratered, scarred by billions of years of asteroid and comet impacts. One of the largest impact basins, called Caloris Basin, spans 1,550 kilometers across. The impact that created it was so powerful that it sent shockwaves through the entire planet, creating strange, hilly terrain on the exact opposite side of Mercury. And yet, despite the scorching daytime temperatures, Mercury has ice. Deep inside craters near its poles, where sunlight never reaches, temperatures remain cold enough to freeze water. Radar observations from Earth and measurements from NASA's Messenger spacecraft confirm the presence of water ice in these permanently shadowed regions. The ice likely came from comets that struck the planet over billions of years. Some of these polar craters also contain organic molecules, the building blocks of life, preserved in the darkness. Messenger, which orbited Mercury from 2011 to 2015, transformed our understanding of the planet. It mapped the entire surface in unprecedented detail, measured the composition of surface rocks, and detected elements like sulfur and potassium that vaporize at relatively low temperatures, suggesting that Mercury didn't form quite as close to the Sun as it is today. The mission also revealed that Mercury is slowly shrinking. As its core cools and contracts, the planet's surface wrinkles like a dried apple, creating cliffs called scarps that stretch for hundreds of kilometers. In 2025, the European Space Agency and Japan's Space Agency launched the Bepi-Colombo mission, which is currently making flybys of Mercury before entering orbit in 2026. This mission will study Mercury's magnetic field in detail, search for more ice deposits, and investigate why such a small planet has such a large iron core. Venus, Earth's so-called sister planet, could not be more different. Similar in size and mass to Earth, Venus is often called our twin. But if Earth is a garden, Venus is a furnace. Its thick atmosphere, composed of 96% carbon dioxide, traps heat so efficiently that surface temperatures reach 465 degrees Celsius, hotter even than Mercury, despite being twice as far from the Sun. This runaway greenhouse effect makes Venus the hottest planet in the solar system. The atmospheric pressure on Venus's surface is 92 times that of Earth, equivalent to the pressure you would experience 900 meters below the ocean surface. This crushing pressure would flatten any unprotected human instantly. The air itself is toxic, laced with sulfur dioxide that forms clouds of sulfuric acid high in the atmosphere. These clouds completely obscure the surface, reflecting so much sunlight that Venus is the brightest planet in Earth's sky, often visible just before sunrise or after sunset. But here's something remarkable. High above the surface, at an altitude of about 50 to 60 kilometers, the temperature and pressure are surprisingly Earth-like. The temperature hovers around 25 degrees Celsius, and the pressure is similar to what we experience at sea level. This region of the atmosphere, despite being filled with sulfuric acid clouds, is one of the most habitable places in the solar system outside of Earth. In 2023 and 2024, researchers made a startling discovery. Certain organic molecules, including amino acids and nucleic acid bases, the building blocks of life, remain stable in concentrated sulfuric acid for weeks without breaking down. This finding suggests that life, if it exists anywhere in the solar system besides Earth, could potentially survive in Venus's clouds. The clouds themselves may even neutralize some of the acid through chemical reactions, creating small pockets where conditions are less hostile. Some scientists have proposed that ammonia, detected tentatively in Venus's atmosphere by Soviet probes in the 1970s, could be a biosignature, a chemical produced by living organisms. On Earth, bacteria produce ammonia as a metabolic byproduct. If life exists in Venus's clouds, it might be doing the same thing, creating a self-sustaining environment by neutralizing the sulfuric acid around it. Venus rotates backward. While most planets spin in the same direction as they orbit the Sun, Venus rotates in the opposite direction, a phenomenon called retrograde rotation. One Venus day lasts 243 Earth days, longer than a Venus year, which is only 225 Earth days. This means the Sun rises in the west and sets in the east, though the thick clouds prevent anyone from actually seeing it. Why Venus rotates backward is still debated. Some scientists think a massive asteroid impact early in the planet's history might have knocked it off kilter. Others propose that gravitational interactions between Venus's thick atmosphere and the Sun could have slowly reversed its rotation over billions of years. Long ago, Venus may have had oceans. Recent research suggests that billions of years ago, when the Sun was younger and dimmer, Venus might have had liquid water on its surface. Models indicate it could have remained habitable for up to 2 billion years before the runaway greenhouse effect took hold. What triggered the transition is unclear. Perhaps it was a series of massive volcanic eruptions that pumped carbon dioxide into the atmosphere, Or perhaps it was a gradual warming as the sun aged and grew brighter. The surface of Venus is young, geologically speaking. Most of it is less than 500 million years old, covered with volcanic plains and lava flows. There are thousands of volcanoes, some over 100 kilometers wide, and vast rift valleys where the crust has split apart. Whether any of these volcanoes are still active is a matter of ongoing debate. Recent observations have detected changes in sulfur dioxide levels in the atmosphere, which could indicate volcanic activity, but confirmation will require more detailed study. Several missions are planned to return to Venus in the coming years. NASA's Veritas and Da Vinci missions and ESA's Envision will study Venus's surface and atmosphere in unprecedented detail, searching for active volcanoes, mapping the composition of surface rocks, and analyzing the chemistry of the clouds. There's even discussion of sending balloon probes that could float in the habitable zone of the atmosphere, directly sampling the clouds for signs of life. Both Mercury and Venus remind us that Earth's habitability is not guaranteed. Small changes in distance from the Sun, atmospheric composition, or geological activity can transform a world from a potential home for life into a scorched, barren wasteland. These inner planets are laboratories where we can study the boundaries of habitability, the fine line between life and lifelessness. Earth and Moon, our cosmic home. Earth is the only known planet with liquid water on its surface. Oceans cover 71% of its area, holding 1.335 billion cubic kilometers of water. This water is why Earth appears blue from space. It moderates our climate, cycles nutrients, and provides the medium in which life first evolved and still thrives today. But Earth wasn't always wet. When it first formed 4.54 billion years ago, it was a molten ball of rock, bombarded constantly by asteroids and comets. The water came later, delivered perhaps by icy comets or by asteroids from the outer solar system that contained water locked in their minerals. The debate over the exact source continues, but the result is clear. Over billions of years, water accumulated, filling low-lying basins and creating the first oceans. Earth has a magnetic field, generated by the motion of molten iron in its outer core. This field extends tens of thousands of kilometers into space, forming an invisible shield called the magnetosphere. The magnetosphere protects Earth from the solar wind and cosmic radiation. Without it, these high-energy particles would strip away the atmosphere and bombard the surface, making life as we know it impossible. The magnetic field also creates auroras. When charged particles from the solar wind penetrate the magnetosphere near the poles, they collide with oxygen and nitrogen atoms in the upper atmosphere, causing them to glow green, red, purple, or blue. These shimmering curtains of light, known as the aurora borealis in the north and aurora australis in the south, are visible from high latitudes and intensify during periods of high solar activity. Earth's atmosphere is unique among the rocky planets. Composed of 78% nitrogen, 21% oxygen, and trace amounts of argon, carbon dioxide, and other gases, it provides the air we breathe and the pressure we need to survive. But the oxygen wasn't always there. For the first 2 billion years of Earth's history, the atmosphere contained almost no oxygen. It was only as. After photosynthetic cyanobacteria evolved and began producing oxygen as a waste product that the atmosphere transformed, paving the way for complex life. The Moon, Earth's only natural satellite, is unusually large relative to its planet. Most moons in the solar system are tiny compared to the worlds they orbit, but the Moon is over a quarter the diameter of Earth. This size has led scientists to sometimes refer to the Earth-Moon system as a double planet, rather than a planet and its satellite. The Moon formed in violence. About 4.5 billion years ago, shortly after Earth itself coalesced from the protoplanetary disk, a Mars-sized object called Theia struck the young Earth in a glancing blow. The impact vaporized part of Earth's mantle, and ejected a massive cloud of debris into orbit. Over time, this debris coalesced under its own gravity, forming the Moon. Evidence for this giant impact hypothesis comes from several sources. Moon rocks, brought back by the Apollo missions, have isotopic compositions nearly identical to Earth's mantle, suggesting they share a common origin. The Moon also has a very small iron core, consistent with it forming from mantle material rather than from a fully differentiated planet. Computer simulations show that a glancing impact by a Mars-sized object could produce a debris disk with just the right properties to form the Moon. The Moon is slowly drifting away from Earth. Tidal forces between the Earth and Moon transfer angular momentum from Earth's rotation to the Moon's orbit, causing the Moon to spiral outward at a rate of about 3.8 centimeters per year. Billions of years ago, the Moon was much closer, appearing much larger in the sky and creating far more powerful tides. These tides have shaped Earth's evolution. The gravitational pull of the Moon causes ocean water to bulge outward on the side facing the Moon and on the opposite side. As Earth rotates beneath these bulges, we experience high and low tides. Over billions of years, the friction from these tides has slowed Earth's rotation. Early in Earth's history, a day was only about 6 hours long. Now it's 24 hours, and it continues to lengthen by about 1.7 milliseconds per century. The Moon is tidally locked to Earth, meaning the same side always faces us. This happened because Earth's gravity created tidal bulges in the Moon's rock, and over time, friction from these bulges slowed the Moon's rotation until it matched its orbital period. The far side of the Moon, often mistakenly called the dark side, is never visible from Earth, though it receives just as much sunlight as the near side. The far side of the Moon looks different from the near side. While the near side has large, dark plains called maria, formed by ancient lava flows, the far side is heavily cratered and mountainous. This asymmetry puzzled scientists for decades until recent research suggested it might be related to the giant impact that formed the Moon. The side facing away from Earth was bombarded more heavily by debris left over from the impact, while the near side remained partially shielded. In 2024, China's Chang'e 6 mission successfully returned samples from the far side of the Moon, the first time any mission has done so. These samples revealed that the far side's volcanic activity occurred earlier and lasted longer than previously thought, providing new clues about the Moon's thermal evolution. The Moon has no atmosphere to speak of, just a thin wisp of gas called an exosphere. Without an atmosphere, there's no weather, no erosion, no sound. Footprints left by Apollo astronauts will remain for millions of years, undisturbed by wind or rain. The temperature swings are extreme. During the lunar day, which lasts about 14 Earth days, temperatures can reach 127 degrees Celsius. During the equally long lunar night, they drop to minus 173 degrees Celsius. Yet the Moon holds water. In permanently shadowed craters near the poles, temperatures never rise above minus 153 degrees Celsius, cold enough to trap water ice for billions of years. Radar observations and spectroscopic measurements have confirmed the presence of water ice in these craters, mixed with the lunar soil. This ice, along with water molecules bound in minerals across the lunar surface, could one day be extracted and used by future human settlements. Earth and the Moon are gravitationally bound partners, each shaping the other. The Moon stabilizes Earth's axial tilt, preventing it from wobbling chaotically and maintaining a relatively stable climate. Without the Moon, Earth's tilt could vary wildly, causing dramatic shifts in seasonal patterns and potentially making life more difficult. The Moon has been a companion to Earth for most of its existence, a silent witness to the rise of continents, the emergence of life, and the evolution of intelligence. It has inspired countless myths, guided travelers across oceans, and driven the tides that shape our shores. Soon, humans will return to its surface, not just to visit, but to stay. The moon is not just Earth's satellite. It is our first step into the cosmos. Mars, the red planet. Mars glows red in the night sky because its surface is covered in iron oxide, common rust. This rusty dust gives the planet its distinctive color and has been oxidized over billions of years, suggesting that Mars once had a thicker atmosphere with more oxygen or water vapor to facilitate the oxidation process. Mars is about half the size of Earth and has only about 1/10 of Earth's mass. Its gravity is much weaker, just 38% of Earth's surface gravity. If you weigh 100 kilograms on Earth, you would weigh only 38 kilograms on Mars. This weak gravity has made it easier for Mars to lose its atmosphere over time. Mars once had rivers. The surface is carved with ancient valley networks, dry riverbeds, and delta-like formations that could only have been created by flowing liquid water. Some of these features are over 3 billion years old, dating from a time when Mars's climate was warmer and wetter. Orbital measurements have even identified minerals like clays and sulfates that form in the presence of water, confirming that liquid water persisted on the surface for extended periods. Recent discoveries have shown that wave ripples found in Martian rock formations could only have been shaped by water open to the atmosphere and acted upon by wind. These ripples, preserved in stone, suggest that Mars once had shallow lakes, not just frozen ice or brief trickles of water. The lakes may have been no more than 2 meters deep, but they were there beneath the sea, beneath a sky that may once have held clouds and rain. So what happened? Why did Mars transform from a world with rivers and lakes into the cold, dry desert we see today? The answer lies in its magnetic field, or rather, its lack of one. Mars is smaller than Earth, and its core cooled faster. About 4 billion years ago, the planet's magnetic field collapsed. Without this protective shield, the solar wind began stripping away the atmosphere, atom by atom, over millions of years. Today, Mars's atmosphere is less than 1% as thick as Earth's, composed mostly of carbon dioxide. The atmospheric pressure is so low that liquid water cannot exist on the surface for long. It either evaporates immediately or freezes. Yet beneath the surface, water persists. Mars has vast reserves of water ice. The polar ice caps, visible even through small telescopes, are made of both carbon dioxide ice and water ice. During the Martian winter, carbon dioxide from the atmosphere freezes onto the caps, and during summer, it sublimes back into the atmosphere. But beneath the seasonal carbon dioxide lies permanent water ice, especially at the North Pole. More recently, spacecraft have discovered enormous deposits of water ice buried beneath the surface at lower latitudes. Radar observations from ESA's Mars Express found evidence of ice deposits up to 3.7 kilometers thick near the equator, beneath layers of dust and volcanic ash. If melted, this ice could cover the entire planet in a layer of water 1.5 to 2.7 meters deep. In 2008, NASA's Phoenix lander confirmed the presence of water ice just beneath the surface at high latitudes. The lander scraped away a few centimeters of soil and found bright white ice, which sublimated away over several days. More recent missions have found ice exposed in fresh impact craters, created when meteorites struck the surface and excavated frozen soil from below. Mars has the largest volcano in the solar system. Olympus Mons rises 21 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. Its base is so wide, over 600 kilometers across, that if you stood on its summit, the horizon would curve away so steeply that you could not see the bottom. Despite its immense height, the slopes of Olympus Mons are gentle, with an average incline of only 5 degrees. Olympus Mons is a shield, volcano, built up gradually by countless eruptions of lava that spread outward in thin sheets. It's located in the Tharsis region, which contains several other massive volcanoes. These volcanoes are no longer active, at least not in recent geological time, but they suggest that Mars once had intense volcanic activity, driven by heat from its interior. Mars also has the longest canyon system in the solar system. Valles Marineris stretches over 4,000 kilometers along the Martian equator, long enough to span the entire United States from coast to coast. In places, it is 7 kilometers deep and 200 kilometers wide. The canyon was likely formed by tectonic forces as the Tharsis region bulged upward, stretching and cracking the crust. Erosion from ancient water flows and landslides have since widened and deepened it. Mars has 2 small moons, Phobos and Deimos. Both are irregularly shaped, more like giant potatoes than spheres, and are thought to be captured asteroids rather than moons that formed alongside Mars. Phobos, the larger of the two, orbits so close to Mars that it completes an orbit in just 7.7 hours, faster than Mars rotates. This means Phobos rises in the west and sets in the east, and it's slowly spiraling inward due to tidal forces. In about 50 million years, it will either crash into Mars or be torn apart by tidal stress, creating a ring around the planet. NASA's Perseverance rover, which landed in Jezero crater in 2021, is searching for signs of ancient microbial life. The crater was once the site of a lake, fed by a river that carved a delta where sediments accumulated. These sediments may have preserved evidence of past life in the form of fossilized microbes or biomarkers, organic molecules associated with biological processes. In 2024, Perseverance found rocks containing minerals and organic molecules that could, possibly, have been produced by ancient microbes. The rover has carefully collected samples of these rocks and stored them in sealed tubes for a future Mars sample return mission, which aims to bring them back to Earth for detailed analysis in laboratories. The search for life on Mars is not limited to the past. Some scientists believe that microbial life could still exist today, deep underground, where liquid water might persist in aquifers warmed by geothermal heat. In 2018, radar data from Mars Express suggested the presence of a subglacial lake of liquid water beneath the southern polar ice cap, though more recent analysis has cast doubt on this interpretation, suggesting the signals might come from layers of clay or other minerals rather than liquid water. Mars's climate is dynamic, even today. Massive dust storms can engulf the entire planet, darkening the sky and lasting for months. These storms are driven by temperature differences between the poles and equator and can reach wind speeds of over 100 kilometers per hour. Though the thin atmosphere means the wind pressure is much weaker than on Earth, the dust can still obscure sunlight, as happened in 2018 when a global dust storm ended the Opportunity rover's mission. Humans will one day walk on Mars. Multiple space agencies and private companies are planning crewed missions within the next 2 decades. The challenges are enormous. The journey takes at least 6 to 9 months each way, exposing astronauts to cosmic radiation and microgravity. Once there, they will need to produce water, oxygen, and fuel from local resources, shelter from radiation, and cope with the psychological isolation of being millions of kilometers from home. But Mars is the most accessible planet beyond Earth, and it holds the potential to answer one of the most profound questions we can ask. Are we alone? The answer may be buried beneath the rusty soil, frozen in ancient lake beds, or waiting deep underground, where liquid water might still flow in the dark. The asteroid belt and small bodies. Between Mars and Jupiter lies a vast region filled with rocky debris, the asteroid belt. It extends from about 2.2 to 3.2 astronomical units from the Sun, though asteroids can be found throughout the inner solar system. Far from being densely packed like some movies suggest, the asteroid belt is mostly empty space. If you were standing on one asteroid, the next nearest one would likely be so far away, you couldn't see it without a telescope. The asteroid belt contains millions of objects, ranging from tiny pebbles to Ceres, a dwarf planet over 900 kilometers in diameter. Despite this vast number, the total mass of all the asteroids combined is only about 4% of the Moon's mass. Most of this mass is concentrated in the four largest objects: Ceres, Vesta, Pallas, and Hygeia. Asteroids are not all the same. They fall into several categories based on their composition. C-type, or carbonaceous. Asteroids are dark and rich in carbon, making up about 75% of known asteroids. S-type, or silicaceous. Asteroids are brighter and composed mainly of silicate minerals and iron. M-type asteroids are metallic, made mostly of iron and nickel, and are thought to be fragments of the cores of larger bodies that were shattered by collisions. These different types tell a story about the conditions in the early solar system. Closer to the Sun, where temperatures were higher, rocky and metallic materials could condense. Farther out, ices and organic compounds could survive, leading to more carbon-rich compositions. The asteroid belt lies at a transition zone, preserving both types of material. Why didn't the asteroids coalesce into a planet? The answer is Jupiter. When Jupiter formed, its immense gravity stirred the asteroid belt, preventing the rocky material from settling into a single large body. Instead, asteroids were flung into eccentric orbits, colliding with each other at high speeds. These collisions shattered larger bodies into fragments, creating the rubble pile we see today. Jupiter's influence continues to shape the asteroid belt. Certain orbital distances correspond to resonances with Jupiter's orbit, where gravitational interactions periodically tug asteroids into new paths. These resonances create gaps in the belt called Kirkwood gaps, named after the astronomer who discovered them. Asteroids that wander into these gaps are usually ejected, either sent crashing into the inner solar system or flung out toward Jupiter. Some asteroids have wandered into Earth-crossing orbits, becoming near-Earth asteroids, or NEAs. These objects pose a potential hazard, and astronomers carefully track thousands of them to predict future impacts. In 2022, NASA's DART mission successfully demonstrated that a spacecraft could deliberately alter an asteroid's trajectory by slamming into it, a technique that might one day be used to deflect an asteroid on a collision course with Earth. Ceres is the largest object in the asteroid belt, and the only one massive enough to be rounded by its own gravity, earning it the classification of a dwarf planet. NASA's Dawn spacecraft orbited Ceres from 2015 to 2018, revealing a world far more complex than expected. The surface is covered with craters, but several bright spots on the floor of Okator crater turned out to be deposits of sodium carbonate, a kind of salt left behind by briny water that had erupted from beneath the surface. Ceres has a subsurface ocean. Beneath its icy crust lies a layer of briny liquid water, kept warm by heat from the interior. This ocean may extend across much of the dwarf planet, making Ceres another potential location to search for simple life, though the conditions are likely far harsher than those in the moons of Jupiter or Saturn. Vesta, the second most massive asteroid, is different from Ceres. It's a rocky, differentiated body with a metallic core, a rocky mantle, and a basaltic crust. It once had volcanic activity, and Dawn's observations revealed vast impact scars, including a crater so deep it exposed the mantle beneath. Meteorites found on Earth, called head meteorites, are fragments of Vesta, blasted off its surface by ancient impacts. Some asteroids have moons. Binary asteroids orbit each other, while others, like Ida, have tiny companions. A few asteroids even have multiple moons. These systems formed either when asteroids collided and the debris remained gravitationally bound, or when rapid rotation caused an asteroid to split apart. Asteroids are time capsules. They are fragments left over from the solar system's formation, largely unchanged, for 4.5 billion years. By studying their composition, scientists can learn what the protoplanetary disk was made of and how the planets formed. Missions like Hayabusa 2 and OSIRIS-REx have collected samples from asteroids Ryugu and Bennu and brought them back to Earth, providing pristine material for analysis. In 2024, the Bennu samples revealed organic molecules and water-bearing minerals, confirming that asteroids delivered the building blocks for life to the early Earth. The molecules included amino acids, sugars, and nucleic acid bases, all essential components of biology. These findings strengthen the hypothesis that life's ingredients came from space, carried by asteroids and comets that bombarded the young Earth billions of years ago. Asteroids may one day be mined for resources. Their metallic cores contain vast quantities of iron, nickel, platinum, and other valuable materials. A single metallic asteroid could contain more platinum than has ever been mined on Earth. While the technology to extract these resources is still being developed, some companies and space agencies are already planning missions to survey promising asteroids. The asteroid belt is not a barrier, but a frontier, filled with small worlds that hold the keys to understanding our origins. These fragments of the early solar system, too small to become planets, remain as witnesses to a time when the solar system was young and chaotic, a swirling disk of dust and rock slowly coalescing into the worlds we see today. Jupiter, king of planets. Jupiter is enormous. It contains more mass than all the other planets combined, over 300 times the mass of Earth. Its volume is so great that 1,300 Earths could fit inside it. Despite this size, Jupiter spins faster than any other planet, completing one rotation in just under 10 hours. This rapid rotation flattens the planet at the poles and bulges it at the equator, giving it a slightly oblate shape. Jupiter is made mostly of hydrogen and helium, the same elements that make up the Sun. If it had been about 80 times more massive, it could have ignited nuclear fusion and become a star. Instead, it's a gas giant, a planet without a solid surface. If you were to descend into Jupiter's atmosphere, you would pass through layers of hydrogen gas that gradually become denser and hotter until, deep below, the hydrogen is compressed so tightly it behaves like a liquid metal. Jupiter's atmosphere is a turbulent, colorful swirl. Bands of white and orange clouds circle the planet, driven by powerful jet streams that reach speeds of over 600 kilometers per hour. These bands are separated by zones of rising and falling gas, creating the striped appearance that makes Jupiter instantly recognizable. The Great Red Spot, a massive storm larger than Earth, has been raging for at least 400 years, and possibly much longer. It rotates counterclockwise, completing one rotation every 6 days, and generates winds exceeding 400 kilometers per hour. Though it has been shrinking over the past century, it remains one of the largest and most persistent storms in the solar system. Jupiter has a powerful magnetic field, 20,000 times stronger than Earth's. This field is generated by the motion of metallic hydrogen in the planet's interior, and it creates a vast magnetosphere that extends millions of kilometers into space. Charged particles trapped in this magnetic field form intense radiation belts around the Sun, a planet far more dangerous than Earth's Van Allen belts. This radiation environment poses challenges for spacecraft. NASA's Juno mission, which has been orbiting Jupiter since 2016, was designed with heavily shielded electronics to survive repeated passes through the radiation belts. Juno has been studying Jupiter's interior structure, magnetic field, and atmosphere, revealing that the planet's core may be partially dissolved and mixed into the surrounding layers, rather than existing as a distinct solid body. Jupiter has at least 95 known moons, more than any other planet in the solar system as of 2023. 4 of these moons are so large they can be seen through binoculars. These are the Galilean moons, discovered by Galileo Galilei in 1610, Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by eruptions of molten sulfur and silicate rock, driven by intense tidal heating. As Io orbits Jupiter, the gravitational pull from the giant planet and its neighboring moons flexes Io's interior, generating enormous amounts of heat. Volcanoes erupt continuously, spewing plumes of sulfur dioxide hundreds of kilometers into space. The surface is painted in vivid yellows, oranges, and reds, the colors of sulfur compounds. Europa is an ice-covered moon about the size of Earth's moon. Its surface is one of the smoothest in the solar system, crisscrossed with cracks and ridges, but remarkably free of large craters. This suggests the surface is young, constantly renewed by geological activity. Beneath the ice lies a global ocean of liquid water, kept warm by tidal heating similar to Io's, though less intense. Europa's ocean may contain more water than all of Earth's oceans combined. Tidal flexing cracks the ice shell, allowing water to well up from below and freeze, resurfacing the moon over millions of years. Chemical analysis by the Galileo spacecraft and more recent observations by the James Webb Space Telescope have detected carbon dioxide on Europa's surface, suggesting that the ocean might contain organic molecules. In October 2024, NASA launched the Europa Clipper mission, designed to make nearly 50 close flybys of Europa, mapping its ice shell, measuring its ocean depth, and searching for active plumes of water erupting from the surface. If such plumes exist, the spacecraft might be able to sample them directly, analyzing their composition for signs of biological activity. Ganymede is the largest moon in the solar system, even bigger than the planet Mercury. It's the only moon known to have its own magnetic field, generated by a liquid iron core. Like Europa, Ganymede likely has a subsurface ocean, sandwiched between layers of ice. Its surface is divided into dark, heavily cratered terrain and brighter grooved regions that appear to have been tectonically reshaped. Callisto, the outermost Galilean moon, is heavily cratered and geologically inactive. Its surface is ancient, dating back billions of years, and it shows little evidence of internal heat. Yet even Callisto may harbor a subsurface ocean, detected through measurements of its magnetic field by the Galileo spacecraft. Beyond the Galilean moons, Jupiter has dozens of smaller moons. Many of these are irregular in shape and orbit in retrograde, suggesting they are captured asteroids or comets rather than moons that formed alongside Jupiter. Discovering and tracking these tiny moons is an ongoing effort, with new ones being identified regularly as telescopes and observational techniques improve. Jupiter acts as a gravitational shield for the inner solar system. Its immense mass deflects many comets and asteroids that might otherwise strike Earth. While Jupiter can also perturb objects into Earth-crossing orbits, on balance, it reduces the number of impacts on Earth by trapping or ejecting potentially dangerous objects. Jupiter may have migrated inward during the early solar system. Simulations suggest that shortly after its formation, Jupiter moved closer to the Sun, disrupting the inner solar system and preventing a large planet from forming in the asteroid belt region. This migration may explain why Mars is so small. Jupiter's gravity disturbed the material that would have otherwise coalesced into a larger planet. Jupiter is still being explored. Juno continues to make close passes, studying the planet's polar regions and discovering that Jupiter's auroras are far more complex than Earth's, driven not just by the solar wind, but also by material ejected from Io's volcanoes. Future missions may include orbiters focused on specific moons, with Europa and Ganymede being top priorities. Jupiter is more than just the largest planet. It is a mini solar system unto itself, a world of swirling storms and volcanic moons, of hidden oceans and ancient surfaces. It reminds us that planets need not be solid to be fascinating, and that the search for life extends far beyond Earth's surface, into the icy shells and briny depths of distant moons. Saturn, Lord of the Rings. Saturn is the second largest planet in the solar system, nearly as large as Jupiter, but much less massive. Its average density is so low that if you could find an ocean large enough, Saturn would float. This is because Saturn is composed mostly of hydrogen and helium, with only a small rocky core deep inside. Like Jupiter, Saturn is a gas giant with no solid surface. Its atmosphere is dominated by hydrogen, with clouds of ammonia crystals creating pale yellow and gold bands around the planet. Winds in Saturn's upper atmosphere reach speeds of 1,800 kilometers per hour, faster even than Jupiter's, whipping around the planet in powerful jet streams. Saturn has a hexagonal storm at its north pole. Discovered by the Voyager spacecraft in the 1980s and studied in detail by Cassini, this hexagon is a bizarre weather pattern where a jet stream flows in a near-perfect six-sided shape. Each side of the hexagon is wider than Earth, and the pattern has persisted for decades, making it one of the most mysterious and enduring features in the solar system. The hexagon rotates with the same period as Saturn's magnetic field, about 10.7 hours, and surrounds a massive hurricane-like vortex at the pole itself. Saturn's rings are its most iconic feature. Spanning over 280,000 kilometers across, but less than 1 kilometer thick in most places, they are composed almost entirely of water ice, with small amounts of rocky material. The ice particles range in size, from grains of sand to chunks as large as houses, all orbiting Saturn in a vast, flat disk. For centuries, scientists assumed the rings were ancient, formed at the same time as Saturn itself, 4.5 billion years ago. But in 2017, Cassini's grand finale changed that view. During its final months, Cassini made 22 daring dives between Saturn and its innermost rings, threading the narrow gap and collecting unprecedented data. By measuring the gravitational pull of the rings on the spacecraft, scientists calculated their mass with high precision. The result was startling. The rings contain only about 40% of the mass of Saturn's moon Mimas, far less than expected. This low mass suggests the rings are young, likely formed only 100 million to 300 million years ago. Further evidence comes from the rate at which micrometeorites darken the rings. Cassini's cosmic dust analyzer measured the influx of sooty particles from interplanetary space bombarding the rings. At the observed rate, the rings would have darkened significantly over billions of years, but they remain bright and icy, indicating they formed relatively recently. So where did the rings come from? The leading theory is that a comet or small moon passed too close to Saturn and was torn apart by tidal forces, the same process that would shred any object crossing Saturn's Roche limit, the distance within which tidal forces overcome an object's self-gravity. Alternatively, a collision between two of Saturn's moons could have produced the debris that became the rings. The rings are not a solid structure. They are divided into several distinct regions separated by gaps. The largest gap, the Cassini division, is 4,800 kilometers wide and is maintained by gravitational resonances with Saturn's moon Mimas. Other gaps are caused by small moons called shepherd moons, which orbit within the rings and use their gravity to clear paths through the ice particles. The rings are also dynamic. Cassini observed waves and ripples moving through them, some caused by moons passing nearby, others by disturbances from within. Temporary features called propellers, created by small moonlets embedded in the rings, appear and disappear as the moonlets orbit and interact with surrounding particles. Cassini discovered that material from the rings is constantly raining down onto Saturn. During its final dives, instruments detected nanometer-sized particles and molecules streaming from the innermost ring into Saturn's atmosphere, pulled by gravity and atmospheric drag. This rain consists mostly of water ice, but also contains organic molecules, hydrocarbons similar to those found in asteroids and comets. At the current rate, the rings are losing material so quickly that they may last only another 100 million years before disappearing entirely. This means we are living at a special time in Saturn's history, witnessing the rings during a brief phase that may never repeat. Saturn has at least 146 known moons, though the exact number keeps changing as more are discovered. The largest moon, Titan, is bigger than the planet Mercury and has a thick atmosphere composed mostly of nitrogen, with traces of methane and ethane. Titan is the only moon in the solar system with a substantial atmosphere, and it's the only place besides Earth where stable liquid exists on the surface. Not water, but lakes and seas of liquid methane and ethane. Titan's surface is hidden beneath a thick orange haze created by photochemical reactions in the upper atmosphere. But radar observations from Cassini pierced through the haze, revealing a complex landscape of lakes, rivers, sand dunes, and mountains. The lakes are found mostly near the poles, filled with liquid hydrocarbons that evaporate, form clouds, and rain back down, creating a hydrological cycle eerily similar to Earth's water cycle. In 2005, the Huygens probe, carried to Titan by Cassini, descended through the atmosphere and landed on the surface. It sent back the first images from the surface of an outer solar system moon, revealing a world of rounded pebbles and drainage channels carved by liquid flows. The temperature at the surface is a frigid minus 179 degrees Celsius, cold enough to freeze methane into ice. Beneath Titan's icy crust may lie a subsurface ocean of liquid water mixed with ammonia, similar to the oceans beneath Europa and Ganymede. This ocean is kept liquid by heat from Titan's interior and by the insulating effect of the thick ice shell above. Whether this ocean could support life is unknown, but Titan remains one of the most promising places to search for extraterrestrial biology. Another moon, Enceladus, is far smaller than Titan, but equally intriguing. Cassini discovered that Enceladus has active geysers erupting from cracks near its south pole, spraying water vapor, ice crystals, and organic molecules into space. These plumes reach hundreds of kilometers high and feed Saturn's E-ring, a diffuse ring of particles far beyond the main rings. Enceladus has a global subsurface ocean, confirmed by measurements of its gravity and the composition of the plume material. The plumes contain salts, silica, and complex organic molecules, suggesting hydrothermal activity on the ocean floor, similar to deep-sea vents on Earth where chemosynthetic life thrives. The presence of hydrothermal vents beneath Enceladus's ice makes it one of the most promising locations in the solar system to search for life. A future mission could fly through the plumes and directly sample the ocean's chemistry, analyzing it for biosignatures without ever needing to drill through the ice. Saturn's moons interact with the rings in complex ways. Tiny moons shepherd the edges of narrow ringlets, while larger moons create gravitational resonances that clear gaps or concentrate particles into clumps. Some moons are made partly from ring material that has accreted onto them over time, creating bizarre shapes with equatorial ridges and smooth, icy surfaces. Cassini operated for 13 years in orbit around Saturn, far exceeding its original mission plan. It made 294 orbits, returned over 450,000 images, and transformed our understanding of the Saturnian system. In 2017, with its fuel nearly exhausted, Cassini was deliberately crashed into Saturn to prevent any chance of contaminating Titan or Enceladus with Earth microbes. Saturn is a world of surprises. Its rings, once thought eternal, are fleeting. Its moons, once thought frozen and dead, harbor oceans and geysers. Its atmosphere, though serene from a distance, seethes with storms and winds that dwarf any on Earth. In Saturn and its moons, we see not just beauty, but a dynamic system still revealing its secrets. Uranus and Neptune. The ice giants. Uranus and Neptune are the solar system's ice giants. While Jupiter and Saturn are made mostly of hydrogen and helium, Uranus and Neptune contain much larger proportions of heavier elements, especially water, ammonia, and methane, all in the form of ices deep in their interiors. This difference in composition places them in a separate category from the gas giants. Uranus is the third largest planet in the solar system, with a diameter about 4 times that of Earth. Its most distinctive feature is its extreme axial tilt. While most planets spin with their rotation axes roughly perpendicular to their orbital planes, Uranus is tilted 98 degrees, meaning it essentially rolls along its orbit like a ball. Its poles experience 42 years of continuous sunlight, followed by 42 years of darkness, creating the most extreme seasons in the solar system. What caused this tilt? The most likely explanation is that Uranus was struck by a massive object early in the solar system's history, knocking it onto its side. Computer simulations suggest the impactor may have been an Earth-sized protoplanet. The collision would have been violent enough to redistribute Uranus's internal heat and possibly vaporize part of its atmosphere. Yet the planet survived, albeit forever altered. Despite its distance from the Sun, Uranus has a surprisingly bland appearance. It appears as a pale blue-green sphere in visible light, with very few clouds or storms visible. The blue-green color comes from methane in its upper atmosphere, which absorbs red light and reflects blue and green. Uranus is cold. Its upper atmosphere reaches temperatures of -224 degrees Celsius, making it the coldest planetary atmosphere in the solar system, even colder than Neptune, despite being closer to the Sun. This suggests that Uranus has very little internal heat. Unlike Jupiter, Saturn, and Neptune, which all radiate more energy than they receive from the Sun, Uranus emits almost no internal heat, a mystery that scientists are still trying to understand. One theory is that the giant impact that tilted Uranus also disrupted its interior, preventing heat from escaping efficiently. Another possibility is that Uranus's interior is layered, with an insulating boundary preventing heat from the core from reaching the surface. Uranus has a faint ring system, discovered in 1977 when astronomers observed the planet passing in front of a distant star. The star's light blinked on and off multiple times before and after Uranus itself occulted it, revealing the presence of narrow rings. Subsequent observations by Voyager 2 and ground-based telescopes have identified 13 rings, all narrow and dark, composed of dust and larger particles. Uranus has 28 known moons, all named after characters from the works of William Shakespeare and Alexander Pope, a unique naming convention among planetary satellites. The 5 largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon, all icy worlds with heavily cratered surfaces. Miranda is one of the strangest moons in the solar system. Its surface is a patchwork of vastly different terrains, with smooth, grooved regions next to heavily cratered highlands. Enormous cliffs, some over 10 kilometers high, tower above the landscape. Scientists believe Miranda may have been shattered by an impact and then reassembled, with pieces of its interior exposed on the surface. Only one spacecraft has visited Uranus, Voyager 2, which flew by in 1986. The encounter revealed a planet more dynamic than expected, with faint cloud bands, a magnetic field tilted 59 degrees from the rotation axis, and a magnetosphere filled with charged particles. But Voyager's visit was brief, lasting only a few hours of closest approach, and much about Uranus remains unknown. Neptune, the 8th and outermost planet, is slightly smaller than Uranus, but more massive. It orbits the Sun at an average distance of 4.5 billion kilometers, so far that it takes 165 Earth years to complete a single orbit. From Neptune, the Sun appears as little more than a very bright star. Despite its distance, Neptune is not bland. It has the strongest winds in the solar system, with jet streams reaching speeds of 2,100 kilometers per hour, faster than the speed of sound on Earth. These winds blow in the opposite direction of the planet's rotation, creating a retrograde jet stream that wraps around Neptune's equator. Neptune's atmosphere displays vivid blue colors, darker and more saturated than Uranus, due to higher concentrations of methane and possibly an unknown compound that absorbs red light. Large storm systems, similar to Jupiter's Great Red Spot, appear and disappear over years or decades. When Voyager 2 visited in 1989, it observed a massive storm called the Great Dark Spot, larger than Earth. But when the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had vanished, replaced by new storms elsewhere. Unlike Uranus, Neptune radiates significant internal heat, about 2.6 times more energy than it receives from the Sun. This internal heat drives the powerful atmospheric dynamics, creating the winds and storms that give Neptune its turbulent appearance. Where this heat comes from is still debated. It may be leftover heat from the planet's formation, slowly leaking out, or it could be generated by gravitational compression as material settles in the interior. Neptune has 16 known moons, the largest of which is Triton. Triton is unusual in several ways. It orbits Neptune backward, in a retrograde direction, and its orbit is slowly decaying due to tidal forces. In about 3.6 billion years, Triton will cross Neptune's Roche limit and be torn apart, creating a spectacular ring system that may rival or surpass Saturn's. Triton is geologically active. Voyager 2 observed geysers of nitrogen gas erupting from the surface, driven by sublimation of nitrogen ice, warmed by the faint sunlight. Triton's surface is young, with very few impact craters, suggesting it has been resurfaced recently by volcanic activity or cryovolcanism, where water or other ices erupt instead of molten rock. Triton likely didn't form alongside Neptune. Its retrograde orbit and composition suggest it was a captured Kuiper Belt object, similar to Pluto. When it was captured, its orbit was highly elliptical, causing intense tidal heating that may have melted its interior and created a subsurface ocean. Over time, the orbit circularized, reducing the tidal heating, but Triton may still harbor a liquid ocean beneath its icy crust. Neptune, like Uranus, has a ring system, though Neptune's rings are fainter and clumpier. Some of the rings contain dense arcs of material, thought to be held in place by the gravity of small moons embedded in the rings. Both Uranus and Neptune remain poorly explored. No spacecraft has visited them since Voyager 2's brief flybys, and no missions are currently planned, though concepts for orbiters and atmospheric probes have been proposed. These ice giants hold clues to how planets form in the outer regions of protoplanetary disks, and their moons may harbor subsurface oceans worth exploring. The ice giants remind us that the solar system is more diverse than the division into rocky and gas planets suggests. They are worlds unto themselves, shaped by different processes, and harboring different mysteries. Their pale blue faces beckon from the edge of the planetary realm, quietly waiting for the day when we return. The Kuiper Belt and Pluto beyond. Neptune lies the Kuiper Belt, a vast ring of icy bodies orbiting in the cold, dim outskirts of the solar system. It extends from about 30 astronomical units just beyond Neptune's orbit, out to roughly 50 astronomical units, though some objects reach much farther. The Kuiper Belt is similar to the asteroid belt, but much larger and contains far more mass, primarily in the form of frozen water, methane, ammonia, and other ices. The Kuiper Belt is home to Pluto, once considered the 9th planet, but reclassified as a dwarf planet in 2006. This reclassification was controversial, but it reflected a deeper understanding of the solar system's structure. Pluto is not alone in the outer solar system. It's one of many Kuiper Belt objects, or KBOs, and not even the largest. Pluto is about 2,170 kilometers in diameter, smaller than Earth's moon. Its orbit is highly elliptical and tilted relative to the plane of the solar system, crossing inside Neptune's orbit at its closest approach to the Sun. Pluto's surface is a patchwork of icy plains, mountains of frozen water ice, and dark, cratered regions covered in ancient nitrogen and methane frosts. In 2015, NASA's New Horizons spacecraft flew past Pluto, providing the first close-up images of the dwarf planet. The images revealed a world far more complex and geologically active than anyone expected. The most iconic feature is a large, heart-shaped region informally named Tombaugh Regio, composed of a smooth plain of frozen nitrogen surrounded by mountains of water ice that rise several kilometers high. Sputnik Planitia, the left lobe of the heart, is a vast basin of nitrogen ice that appears to be geologically young, with no impact craters. Scientists believe this ice is constantly being recycled by convection, where warmer ice from below rises to the surface while cooler ice sinks, creating a slow, churning motion. This activity requires an internal heat source, possibly driven by radioactive decay in Pluto's core or by tidal interactions with its largest moon, Charon. Charon is about half the size of Pluto, making the Pluto-Charon system more like a double planet than a planet and its satellite. The two are tidally locked, always showing the same face to each other as they orbit their common center of mass. Charon's surface is less colorful than Pluto's, dominated by gray water ice, but it has a distinctive dark red polar cap, thought to be made of organic molecules called tholins, created by radiation processing of methane ice. Pluto has 5 known moons: Charon, Styx, Nix, Kerberos, and Hydra. The smaller moons are irregularly shaped and orbit in the same plane as Charon, likely formed from debris created during the collision that formed the Pluto-Charon system billions of years ago. The Kuiper Belt contains several other large objects. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive, one of the factors that led to Pluto's reclassification. Makemake and Haumea are other notable dwarf planets, each with their own unique characteristics. Haumea, for example, is shaped like a flattened ellipsoid, spinning so rapidly that it completes a rotation every 4 hours, and it has a ring system, making it the smallest known body with rings. Kuiper Belt objects are thought to be remnants from the solar system's formation, primordial material that never coalesced into a planet. Because they formed in the cold outer regions, they preserved ices and organic compounds that would have been driven off closer to the Sun. Studying these objects gives scientists a window into the conditions that existed 4.5 billion years ago. Some Kuiper Belt objects have highly eccentric orbits that bring them into the inner solar system periodically. These are short-period comets, with orbital periods less than 200 years. As they approach the Sun, the ices on their surfaces sublimate, creating glowing comas and tails that can stretch millions of kilometers. In 2025, astronomers proposed the existence of a hypothetical planet lurking in the far outer solar system, dubbed Planet Y or Planet 9. This hypothetical world would be smaller than Neptune, but larger than Earth, orbiting at hundreds of times Earth's distance from the Sun. Its existence is inferred from the unusual orbits of certain distant Kuiper Belt objects, which cluster in ways that suggest they are being gravitationally perturbed by an unseen planet. While Planet Y has not been directly observed, the search continues. The Vera C. Rubin Observatory, set to begin operations soon, will survey the sky with unprecedented sensitivity, potentially revealing this hidden world or ruling out its existence. The Kuiper Belt also contains scattered disk objects, KBOs with highly elliptical and inclined orbits. These objects likely formed closer to the Sun, but were scattered outward by gravitational interactions with Neptune during the solar system's early evolution. Eris is one such object, as is Sedna, a distant dwarf planet with an orbit so elongated it takes over 11,000 years to complete. Some scientists believe Sedna's unusual orbit suggests it was influenced by a passing star early in the solar system's history, or possibly by the hypothetical Planet Y. Sedna's perihelion is so distant that it never comes close enough to Neptune to be affected by its gravity, raising questions about how it ended up in such an orbit. The Kuiper Belt is not a static collection of frozen rocks. It's a dynamic region shaped by gravitational interactions with the giant planets, collisions between objects, and the slow process of orbital migration. Over billions of years, the structure of the Kuiper Belt has changed, and it continues to evolve today. One day, a mission may return to the Kuiper Belt to explore more of its denizens. Concepts for a Kuiper Belt orbiter have been proposed, which would visit multiple objects, studying their compositions, surfaces, and internal structures. Such a mission could reveal whether subsurface oceans exist in some larger KBOs, and whether the building blocks of life are present in these frozen worlds. The Kuiper Belt marks the edge of the planetary solar system, but beyond it lies even more. It is the boundary between the realm of the planets and the vast, cold expanse that extends toward the stars. Solar system formation and evolution. The solar system formed from a cloud of gas and dust called the solar nebula. About 4.6 billion years ago, a disturbance, perhaps a nearby supernova shockwave, caused a region within a larger molecular cloud to collapse under its own gravity. As the cloud collapsed, it began to spin, and the conservation of angular momentum caused it to flatten into a disk. At the center of this disk, material accumulated and heated, eventually forming a protostar. As the protostar grew, temperatures and pressures at its core increased until hydrogen fusion ignited, and the sun was born. Surrounding the young sun was a protoplanetary disk, a swirling plain of dust and gas that would eventually give rise to the planets. The temperature of the protoplanetary disk varied with distance from the sun. Close to the sun, temperatures were high enough to vaporize most ices, leaving only metals and rocky minerals that could condense. Farther out, beyond the frost line, temperatures were low enough for water ice and other volatile compounds to freeze, allowing much more mass to accumulate. In the inner solar system, particles of dust and rock collided and stuck together through electrostatic forces and low-velocity impacts, forming larger and larger clumps. These clumps, called planetesimals, ranged from meters to kilometers in size. Over time, planetesimals collided and merged, growing into protoplanets through a process called accretion. Accretion was not gentle. Collisions between planetesimals generated enormous amounts of heat, melting their interiors. Denser materials, like iron, sank to the center, forming metallic cores, while lighter materials, like silicate minerals, floated to the surface, creating rocky mantles and crusts. This process, called differentiation, shaped the internal structures of the terrestrial planets. The Earth-Moon system formed during one of these violent collisions. About 4.5 billion years ago, a Mars-sized protoplanet called Theia struck the young Earth. The impact vaporized Theia and part of Earth's mantle, ejecting a massive cloud of debris into orbit. This debris coalesced over time, forming the Moon. In the outer solar system, beyond the frost line, ice greatly increased the amount of material available for planet formation. Planetesimals grew more rapidly, and some reached 10 to 15 Earth masses, massive enough to gravitationally capture surrounding hydrogen and helium gas from the protoplanetary disk. These became the cores of Jupiter and Saturn, which accumulated vast atmospheres, transforming into gas giants. Jupiter's formation had profound effects on the rest of the solar system. As it grew, its gravity stirred the asteroid belt, preventing the material there from coalescing into a planet. Jupiter also migrated inward, moving closer to the Sun in a process called planetary migration. This migration disrupted the orbits of planetesimals throughout the solar system, sending some crashing into the Sun, others flung outward, and some redirected toward the inner planets. Computer simulations suggest that Jupiter's inward migration may have lasted for a few 100,000 years before Saturn formed, and the two planets became locked in a gravitational resonance. This resonance reversed Jupiter's migration, causing both planets to drift outward to their current positions. This scenario, known as the Grand Tack hypothesis, helps explain why Mars is so small and why the asteroid belt has the structure it does today. Uranus and Neptune formed farther out, where the disk was less dense and accretion slower. They may have formed closer to Jupiter and Saturn and been scattered outward by gravitational interactions, a process that would have taken millions of years. During this scattering, Uranus and Neptune likely passed through the primordial Kuiper belt, ejecting most of the material there and leaving behind only a small fraction of what originally existed. The early solar system was a chaotic and violent place. For the first few 100 million years after the planets formed, they continued to be bombarded by leftover planetesimals. This period, known as the Late Heavy Bombardment, peaked around 3.9 billion years ago, pockmarking the surfaces of the Moon, Mercury, Mars, and even Earth with craters, some of which remain visible today. The bombardment may have delivered water to Earth, while some of Earth's water likely came from minerals in the original planetesimals that formed the planet. Isotopic analysis of comets and asteroids suggests that a significant fraction was delivered by impacts during the Late Heavy Bombardment. These same impacts may have also delivered organic molecules, the building blocks of life. The solar system continued to evolve after the bombardment ended. Asteroids and comets occasionally collide with planets even today, and planetary orbits slowly shift due to gravitational interactions. The Yarkovsky effect, where sunlight absorbed and re-emitted as heat creates a tiny thrust, can alter the orbits of small asteroids over millions of years. The Sun itself has evolved. When it first ignited, it was about 70% as bright as it is today. Over billions of years, as hydrogen fusion in the core converts hydrogen into helium, the Sun has gradually grown brighter and will continue to do so. This increase in brightness has had profound effects on the planets. Early Mars may have been warm enough for liquid water because the Sun was dimmer, and as the Sun continues to brighten, Earth will eventually become too hot for liquid water to exist on the surface. The solar system will not remain as it is forever. In about 5 billion years, the Sun will exhaust the hydrogen in its core and begin fusing helium into heavier elements. It will swell into a red giant, engulfing Mercury, Venus, and possibly Earth. The outer planets will be spared, but their moons will experience drastically different environments. Titan and Europa, currently frozen, may warm enough for their subsurface oceans to become surface oceans. After the red giant phase, the Sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas that will drift outward into space. What remains will be a white dwarf, a dense, Earth-sized remnant that will slowly cool over trillions of years. The planets that survive will orbit this dying ember in the darkness, their surfaces cold and lifeless, witnesses to the Sun's final transformation. The story of the solar system's formation and evolution is one of violence and creation, of chaos gradually giving way to order. From a cloud of gas and dust emerged a star and its family of planets, each one shaped by the conditions of its birth and the long, slow processes of time. We are part of this story, made from the same materials that formed the Sun and planets, residents of a system still writing its history. The outer reaches beyond the Kuiper belt lies the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system. Unlike the Kuiper belt, which is a relatively flat disk, the Oort cloud extends in all directions, forming a distant boundary between the Sun's gravitational influence and interstellar space. The Oort cloud is thought to contain trillions of comets, ranging in size from a few meters to tens of kilometers across. These comets formed closer to the Sun during the solar system's early history, but were ejected into distant orbits by gravitational interactions with the giant planets. Over billions of years, they settled into a vast halo that extends from about 2,000 astronomical units to as far as 100,000 astronomical units, nearly halfway to the nearest star. Most of the time, Oort cloud comets remain frozen and inactive, dormant relics drifting in the dark. But occasionally, gravitational perturbations from passing stars, molecular clouds, or the Milky Way's tidal forces nudge a comet's orbit, sending it plunging toward the inner solar system. As the comet approaches the Sun, solar radiation warms its surface, causing ices to sublimate and creating the glowing coma and tail that make comets visible from Earth. Long-period comets, those with orbital periods greater than 200 years, originate from the Oort cloud. Some have orbital periods of millions of years, and may visit the inner solar system only once in human history. Comet Hale-Bopp, visible in 1997, and Comet Neowise, visible in 2020, are examples of long-period comets that captivated observers around the world. Short-period comets, like Halley's Comet, which returns every 75 to 76 years, come from the Kuiper Belt. These comets have been captured into shorter orbits by gravitational interactions with the giant planets, especially Jupiter. Over time, repeated passes close to the Sun deplete their volatile ices, and they eventually become inactive, appearing more like asteroids than comets. Comets are important to scientists because they are pristine samples of the material from which the solar system formed. Their ices and dust contain organic molecules, amino acids, and other compounds that may have seeded the early Earth with the building blocks of life. Missions like ESA's Rosetta, which orbited Comet 67P Churyumov-Gerasimenko from 2014 to 2016, have revealed that comets are far more complex than simple dirty snowballs, containing layered structures, varied compositions, and even organic molecules. In recent years, astronomers have detected interstellar visitors passing through the solar system. The first confirmed interstellar object, Oumuamua, was discovered in 2017. Its trajectory showed it was not bound to the Sun, having originated from another star system. Oumuamua was elongated, tumbling through space, and exhibited a slight acceleration that could not be explained by gravity alone, possibly due to outgassing as it was warmed by the Sun. In 2019, a second interstellar object, Comet 2I Borisov, was discovered. Unlike Oumuamua, which appeared rocky or metallic, Borisov had a visible coma and tail, confirming it was a comet. Its composition, measured spectroscopically, was similar to comets from the Oort cloud, suggesting that comets around other stars are chemically similar to those in our own solar system. The detection of these interstellar objects suggests that countless such objects drift through the galaxy, ejected from their home systems and wandering alone through the void. Future surveys may detect many more, offering opportunities to study material from other planetary systems without ever leaving our own. The solar system's boundary is defined by the heliosphere, a bubble of space dominated by the solar wind. The solar wind, a constant stream of charged particles from the Sun, flows outward in all directions, creating a protective cocoon around the planets. This cocoon shields the solar system from the interstellar medium, the tenuous gas and cosmic rays that fill the space between stars. The heliosphere has a distinct boundary called the heliopause, the point where the solar wind's pressure is balanced by the pressure of the interstellar medium. Beyond the heliopause, the solar wind ceases, and the environment becomes truly interstellar. In 2012, Voyager 1 became the first human-made object to cross the heliopause, entering interstellar space at a distance of about 122 astronomical units from the Sun. Voyager 2 followed in 2018, crossing at a different location and providing comparative data. Both spacecraft continue to transmit data, measuring the properties of the interstellar medium and sending back information about this uncharted region. The heliosphere is not spherical. It's shaped like a teardrop, compressed on the side, facing the sun's motion through the galaxy and stretched into a long tail on the opposite side. This tail, called the heliotail, extends for hundreds of astronomical units behind the solar system, a cosmic wake left by the sun's journey through space. The Voyager spacecraft, launched in 1977, have traveled farther from Earth than any other human-made objects. They carry golden records, phonograph discs containing sounds, music, and images from Earth, intended as messages to any intelligent beings that might one day encounter them. The likelihood of the records ever being found is infinitesimally small, but their presence is a testament to humanity's desire to reach out, to say, "We were here. This is who we are." Both Voyagers are powered by radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity. As the plutonium decays, the power output gradually decreases. Scientists estimate that by the 2030s, the spacecraft will no longer have enough power to operate their instruments, and communication will cease. They will continue to drift through interstellar space, silent and dark, for billions of years. The solar system does not end abruptly at the heliopause. The Oort cloud extends far beyond, and the sun's gravity influences objects even farther out. Sedna, a distant dwarf planet, orbits at such a great distance that it spends most of its orbit well beyond the Kuiper belt, in a region that may overlap with the inner Oort cloud. Some scientists speculate that there may be a region called the inner Oort cloud, or Hills cloud, a disc-shaped collection of comets closer than the main Oort cloud. If it exists, this region would contain objects that are easier to reach than those in the main Oort cloud, making them potential targets for future exploration. The solar system is a tiny island in the vastness of space, but it is our island. It contains everything we have ever known, every person who has ever lived, every story ever told. And yet it occupies only a minuscule fraction of the Milky Way galaxy, which itself is only one of hundreds of billions of galaxies in the observable universe. From the sun's burning core to the frozen reaches of the Oort cloud, the solar system is a place of astonishing diversity. It is a laboratory where we can study planetary formation, atmospheric dynamics, and the potential for life beyond Earth. It is a frontier, beckoning us to explore, to discover, to understand. And it is home. Closing. And now, as the journey through the solar system gently draws to a close, let the vastness settle around you like a soft blanket. We've drifted through the sun's blazing corona, past scorched Mercury and cloud-wrapped Venus, visited our own Earth and Moon, and wandered across the rusty plains of Mars. We've sailed through the asteroid belt, stood in the shadow of Jupiter's great red spot, and marveled at Saturn's fleeting rings. We've ventured to the ice giants, Uranus and Neptune, crossed the Kuiper belt, and touched the edge of interstellar space. 100 facts, perhaps a few more, each one a thread in the vast, intricate weaving of our cosmic neighborhood. Some surprising, some familiar, but all part of the story of where we come from and what surrounds us. You are made of star stuff. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in the hearts of stars that lived and died long before the sun was born. You are not separate from the solar system. You are part of it, a small but essential piece of the ongoing story. If these quiet facts helped you unwind, if they offered you a moment of peace or a spark of curiosity, please consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. The solar system will continue its slow, patient dance long after we are gone. Planets will orbit. Moons will rise and set. Comets will sweep through the inner realm, trailing glowing tails. The sun will shine, steady and warm, for billions of years yet to come. Sleep well, knowing that you drift through space on a small blue world, cradled in the arms of gravity, carried through the dark by a star that has watched over us since the beginning. Good night, and thank you for exploring the wonders of our solar system with me. Additional facts: the solar system's hidden wonders. The solar system is filled with countless marvels that deserve exploration. Let's delve deeper into some of the most fascinating discoveries and ongoing mysteries. The dance of orbital resonances. Gravity doesn't just pull objects in straight lines. It creates intricate patterns, resonances that lock planets and moons into precise mathematical relationships. Jupiter and Saturn, for example, nearly complete 5 orbits for every 2 of Saturn's, a 5.2 resonance that has stabilized their orbits for billions of years. This resonance prevents close encounters that might otherwise destabilize the outer solar system. The Galilean moons of Jupiter exhibit even more precise resonances. For every 4 orbits, Io completes around Jupiter. Europa completes exactly 2, and Ganymede completes exactly 1. This 4-2-1 resonance, called the Laplace resonance after the mathematician who first described it, creates the tidal heating that powers Io's volcanoes and keeps Europa's ocean liquid. The moons tug on each other in precisely timed intervals, pumping energy into their interiors through gravitational flexing. Even the asteroid belt shows the fingerprints of orbital resonances. The Kirkwood gaps, regions notably devoid of asteroids, occur at orbital distances, where asteroids would have periods that are simple fractions of Jupiter's period. An asteroid at the 3-1 resonance, for example, completes 3 orbits for every one of Jupiter's. Over millions of years, repeated gravitational tugs from Jupiter at the same point in the sheet. Asteroids' orbit gradually pump energy into its motion, increasing its eccentricity until it's ejected from that orbital region entirely. These resonances aren't just mathematical curiosities. They shape the architecture of planetary systems, determining which orbits are stable and which are chaotic. They concentrate ring particles around Saturn into narrow ringlets. They carve gaps in protoplanetary disks, creating the conditions for planets to form. Resonances are the solar system's hidden choreographers, the invisible hands that arrange worlds into enduring patterns. The mystery of planetary magnetism. Earth is not the only world with a magnetic field. Mercury, Jupiter, Saturn, Uranus, and Neptune all generate their own magnetic fields through dynamo processes in their interiors. But the details vary dramatically from world to world. Mercury's magnetic field is surprisingly weak for a planet with such a large iron core. It's only about 1% the strength of Earth's field. This weakness may be because Mercury's core is partially solidified, or because the planet rotates so slowly that the dynamo process is less efficient. Yet despite its weakness, Mercury's field is enough to create a small magnetosphere that deflects some of the solar wind. Jupiter's magnetic field is the strongest in the solar system, more than 20,000 times stronger than Earth's. It's generated not by an iron core, but by convection of metallic hydrogen in the planet's interior. This enormous field creates a magnetosphere so vast it would appear larger than the full moon from Earth if it were visible to the naked eye. The radiation belts within Jupiter's magnetosphere are so intense they can damage spacecraft electronics, a major engineering challenge for any mission to the Jovian system. Saturn's magnetic field is nearly perfectly aligned with its rotation axis, an unusual configuration that scientists don't fully understand. Most planets have significant tilts between their magnetic and rotational poles, but Saturn's are aligned to within 1 degree. This perfect alignment may result from the way the dynamo operates deep within Saturn's metallic hydrogen layer. Uranus and Neptune have bizarre magnetic fields. Both planets' fields are tilted dramatically from their rotation axes, by 59 degrees and 47 degrees respectively, and both are offset from the planet's centers. This suggests their magnetic fields are generated not deep in their cores, but in relatively shallow layers of their interiors, perhaps in regions where water, ammonia, and methane exist in electrically conductive states under high pressure. Mars once had a magnetic field, but lost it about 4 billion years ago, when its core cooled and solidified. The loss of this protective field allowed the solar wind to strip away much of Mars's atmosphere over billions of years, transforming it from a warm, wet world into the cold, dry desert we see today. Ancient crustal magnetism remains frozen in certain regions of Mars's surface, geological scars from a time when the planet's interior was still molten and dynamic. Venus has no magnetic field at all, despite being similar in size to Earth. The reason is still debated. Venus may rotate too slowly for its core to generate a dynamo, or perhaps its core lacks the right combination of liquid metal and convective motion. Without a magnetic field, Venus's upper atmosphere is directly exposed to the solar wind, which slowly strips away atmospheric particles, though at a much slower rate than on Mars, because Venus's thick atmosphere provides some protection through sheer mass. Understanding planetary magnetism helps scientists reconstruct the thermal and chemical evolution of planets. A strong magnetic field indicates an active interior with ongoing convection. A weak or absent field suggests a cooling, perhaps dying world. These magnetic signatures tell stories of planetary histories written in the orientation and strength of invisible fields. Water everywhere. Water is far more common in the solar system than early astronomers imagined. We find it not just on Earth, but frozen in the polar caps of Mars, buried beneath the surfaces of icy moons, and possibly even in the atmospheres of giant planets. Europa's subsurface ocean may contain twice as much water as all of Earth's oceans combined. The ice shell above it is estimated to be 15 to 25 kilometers thick, beneath which lies a global ocean perhaps 100 kilometers deep. Tidal heating from Jupiter keeps this ocean liquid, and cracks in the ice allow material to exchange between the surface and the depths below. Recent observations have detected water vapor plumes erupting from Europa's surface, offering the tantalizing possibility of sampling the ocean's chemistry without ever needing to drill through the ice. Enceladus, Saturn's sixth largest moon, also has a subsurface ocean, confirmed by measurements of its gravity and the composition of the water vapor plumes that erupt from fractures near its south pole. These plumes contain not just water, but also salts, silica particles, and organic molecules, suggesting hydrothermal activity on the seafloor. The discovery of molecular hydrogen in the plumes indicates that water is reacting with rocks in Enceladus's core, potentially creating environments similar to Earth's deep-sea hydrothermal vents, where chemosynthetic life thrives without sunlight. Ganymede likely has a multi-layered internal structure, with several distinct layers of ice and liquid water stacked like a sandwich. The pressure at great depths is so high that water ice exists in exotic crystalline forms denser than liquid water. These high-pressure ice layers might sit atop deeper oceans, creating complex internal structures unlike anything on Earth. Even Ceres, the largest asteroid, harbors a subsurface ocean, or at least a layer of briny mud beneath its icy crust. Bright deposits of sodium carbonate on Ceres' surface indicate that briny water has recently erupted from below, freezing as it reaches the surface and leaving behind mineral deposits. Beyond the major moons, water ice is ubiquitous. It forms the cores of comets, coats the surfaces of Kuiper belt objects, and fills permanently shadowed craters at the poles of Mercury and the Moon. Water is the second most abundant molecule in the universe after molecular hydrogen, and wherever temperatures are low enough, it condenses into ice. The solar system is awash in water, most of it frozen, but some of it liquid. hidden beneath icy crusts, waiting to be explored. The architecture of planetary atmospheres. Atmospheres are more than blankets of air. They're dynamic systems shaped by temperature, pressure, rotation, and the interaction with solar radiation and planetary surfaces. Each atmosphere in the solar system is unique, reflecting the planet's size, distance from the sun, and geological history. Earth's atmosphere is the only one rich in free oxygen, a byproduct of photosynthetic life that has fundamentally altered the planet's chemistry. Oxygen is highly reactive and would disappear in a geological instant, if not constantly replenished by living organisms. The presence of large amounts of oxygen in Earth's atmosphere is itself a biosignature, a sign of life that could theoretically be detected from distant exoplanet observations. Venus's atmosphere is thick and oppressive, with a surface pressure 92 times that of Earth and temperatures hot enough to melt lead. But high in the atmosphere, conditions are surprisingly Earth-like. At altitudes of 50 to 60 kilometers, temperatures hover around 25 degrees Celsius, and pressures are roughly equivalent to sea level on Earth. This region of the atmosphere could potentially be hospitable to microbial life, floating in sulfuric acid clouds, but adapted to use the acid as a solvent. Mars's thin atmosphere is mostly carbon dioxide, with a surface pressure less than 1% of Earth's. This low pressure means liquid water cannot exist on the surface for long. It either freezes or evaporates. Yet Mars's atmosphere is surprisingly active. Dust devils whirl across the plains. Clouds of water ice form over mountains. Seasonal changes drive the sublimation and deposition of carbon dioxide ice at the poles, causing the atmospheric pressure to vary by up to 30% between winter and summer. Titan's thick nitrogen atmosphere is even denser than Earth's, with a surface pressure 1.5 times greater. The atmosphere is so thick and the gravity so low that humans could fly on Titan using wings attached to their arms. Methane plays the role on Titan that water plays on Earth, evaporating from lakes, forming clouds, and raining back down. Complex organic molecules called tholins, created by ultraviolet light breaking apart methane, give the atmosphere its orange haze. Jupiter and Saturn's atmospheres are layered with clouds of different compositions at different altitudes. Ammonia. Ice clouds float highest, followed by ammonium hydrosulfide clouds, and then water ice clouds deeper down. Below the visible cloud layers, the atmosphere gradually transitions from gas to liquid as pressure increases, eventually becoming a supercritical fluid that is neither fully gaseous nor fully liquid. Uranus and Neptune have methane-rich atmospheres that give them their distinctive blue-green colors. The methane absorbs red light and reflects blue and green wavelengths. But there's likely another unknown compound, possibly a sulfur-based molecule or a high-altitude haze, that enhances the blue color, especially on Neptune. Understanding planetary atmospheres is crucial for understanding climate, weather, and habitability. The thin line between a life-supporting atmosphere and a lifeless one is determined by factors we're still learning to predict, factors that may determine which worlds we can one day call home. The role of impacts in shaping worlds. Impacts have shaped the solar system more than any other single process. Every solid surface bears the scars of bombardment, from tiny micrometeorite pits to vast basins hundreds of kilometers across. These impacts aren't just destructive, they've also delivered water, organic molecules, and perhaps even the seeds of life to Earth and other worlds. The Moon's surface is a museum of impacts, preserving craters from 4 billion years ago because it has no atmosphere to erode them. The largest lunar impact basin, the South Pole Aitken Basin, spans over 2,500 kilometers and is one of the largest impact structures in the solar system. The impact that created it was so powerful, it may have excavated material from the Moon's mantle, providing a unique window into the interior composition. Earth experiences impacts too. though most craters have been erased by erosion, plate tectonics, and volcanic activity. About 66 million years ago, an asteroid roughly 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact released energy equivalent to billions of nuclear bombs, triggering massive wildfires, tsunamis, and a global winter that lasted for years. This event is widely believed to have caused the extinction of the dinosaurs and many other species, fundamentally altering the course of evolution on Earth. Mars bears the scars of ancient mega impacts. The Hellas Basin, 2,300 kilometers across and 7 kilometers deep, is one of the largest impact craters in the solar system. The impact that created it may have occurred during the late heavy bombardment, about 4 billion years ago. Material ejected from such large impacts can travel enormous distances, sometimes even escaping Mars's gravity entirely. Meteorites found on Earth that originated from Mars were blasted off the planet by impacts millions of years ago, traveled through space, and eventually fell to Earth. The asteroid belt itself is the product of countless impacts. Larger bodies were shattered into fragments, creating families of asteroids that share similar orbits and compositions. The breakup of these parent bodies released vast amounts of debris that continue to collide and grind into smaller pieces. Over time, the asteroid belt has transitioned from a region of planet formation to a cosmic demolition derby. Even the gas giants have been impacted. In 1994, comet Shoemaker-Levy 9 broke apart and collided with Jupiter in a series of impacts that created dark scars in Jupiter's atmosphere visible from Earth. The impacts released energy equivalent to millions of megatons of TNT, demonstrating that even the largest planets are not immune to cosmic bombardment. Impacts continue today, though at a much reduced rate compared to the early solar system. Near-Earth asteroids occasionally pass close to Earth, and tracking them has become a priority for planetary defense. In 2013, a small asteroid about 20 meters in diameter exploded over Chelyabinsk, Russia, releasing energy equivalent to about 500 kilotons of TNT. The shockwave injured over 1,500 people, mostly from broken glass. This event highlighted the ongoing need to monitor the sky for potential impactors. The study of impacts is not just about understanding destruction. Impacts delivered water and organic molecules to the early Earth, possibly making life possible. They excavate subsurface material, allowing scientists to study the interiors of planets without drilling. They create conditions of extreme temperature and pressure, forming unique minerals and structures. And they remind us that the solar system is still a dynamic, sometimes violent place, where the past is written in craters and the future remains uncertain. The future of solar system exploration. The solar system is no longer an abstract concept studied only from afar. It's becoming a neighborhood we can visit, explore, and perhaps one day inhabit. The coming decades will see an unprecedented expansion of human and robotic presence throughout the solar system, driven by scientific curiosity, technological advancement, and the eternal human desire to explore the unknown. NASA's Artemis program aims to return humans to the moon by the late 20s, establishing a sustainable presence on and around Earth's nearest neighbor. Unlike the Apollo program, which consisted of brief visits, Artemis is designed to create permanent infrastructure. The Lunar Gateway, a small space station in orbit around the moon, will serve as a staging point for surface missions. Astronauts will descend to the lunar surface for extended stays, conducting science, testing technologies, and searching for water ice in permanently shadowed craters. The water ice at the lunar poles is more than just a scientific curiosity. It's a resource. Water can be split into hydrogen and oxygen, providing rocket fuel and breathable air. It can support long-duration missions without requiring everything to be launched from Earth. So, presence of water on the moon fundamentally changes the economics of space exploration, making the moon a potential stepping stone to more distant destinations. Mars remains the ultimate goal for human exploration. multiple space agencies and private companies are developing plans for crewed missions to the Red Planet. The challenges are immense. A round-trip mission to Mars takes at least 2 to 3 years, exposing astronauts to cosmic radiation, microgravity, and the psychological stress of isolation. Once there, they'll need to produce water, oxygen, and fuel from local resources, shelter from radiation and dust storms, and cope with the 6-month communication delay with Earth. But these challenges are not insurmountable. Technologies are being developed to address each one. Habitats could be built using Martian regolith for radiation shielding. Water ice beneath the surface could be extracted and purified. The Martian atmosphere, though thin, is mostly carbon dioxide, which can be processed to produce oxygen and methane fuel through the Sabatier reaction. Plants could be grown in greenhouses, providing food and recycling carbon dioxide into oxygen. The first humans to set foot on Mars will likely spend 500 days on the surface before the planets align favorably for the return journey. During that time, they'll explore Jezero Crater or another geologically rich location, drill for subsurface water, search for signs of past life, and lay the groundwork for future settlements. They'll experience sunrises that paint the sky pink instead of blue, watch Phobos race across the sky 3 times a day, and stand in a world where no human has stood before. Beyond Mars, the moons of Jupiter and Saturn beckon. Europa Clipper, launching in 2024, will make nearly 50 flybys of Europa, mapping its ice shell and searching for active water plumes. If plumes are found, a follow-on mission could fly through them and sample the ocean's chemistry directly, searching for biosignatures without ever needing to land. Future missions might deploy ice-penetrating robots that burrow through the ice shell and swim in the ocean below, exploring one of the solar system's most promising abodes for life. Titan, with its thick atmosphere and surface lakes of liquid methane, is another high-priority target. NASA's Dragonfly mission, a nuclear-powered rotorcraft, will launch in 2028 and arrive at Titan in the mid-2030s. It will fly from location to location, sampling the surface and searching for prebiotic chemistry, the organic molecules that might lead to the origin of life. Titan is a world of unparalleled organic chemistry, a natural laboratory where the building blocks of life are being synthesized in vast quantities. Even more distant destinations are being considered. A mission to Triton, Neptune's largest moon, could reveal whether its subsurface ocean is habitable and study the geysers that erupt from its surface. A mission to Uranus or Neptune could transform our understanding of ice giant planets, a category that is common around other stars but poorly understood in our own solar system. Private companies are also entering the space of deep space exploration. SpaceX's Starship, designed to be fully reusable, could dramatically reduce the cost of sending large payloads to the Moon, Mars, and beyond. Blue Origin is developing the Blue Moon lander for lunar cargo delivery. Other companies are proposing mining operations on asteroids, extracting valuable metals like platinum and rare earth elements. The idea of space mining may sound like science fiction, but the economics could be compelling. A single metallic asteroid could contain more platinum than has ever been mined on Earth. While the initial costs would be enormous, the long-term potential for resource extraction could fund further exploration and development. Water extracted from asteroids could be used to refuel spacecraft, creating a network of orbital depots that make deep space more accessible. Human expansion into the solar system will not happen overnight. It will unfold over decades, perhaps centuries, driven by small steps that gradually extend our reach. Permanent bases on the Moon will come before settlements on Mars. Robotic missions to the outer solar system will pave the way for eventual human exploration. Each generation will build on the accomplishments of the previous one, pushing the boundaries of what's possible. But expansion is not without ethical considerations. How do we protect potentially habitable environments from contamination by Earth microbes? The planetary protection protocols developed by international space agencies aim to prevent biological contamination. But as missions become more complex and commercial interests grow, maintaining these standards will be challenging. The discovery of life, even microbial life, on another world would be one of the most profound scientific discoveries in history. We must ensure our exploration doesn't destroy what we're seeking to find. There's also the question of how we govern activities in space. The Outer Space Treaty of 1967 established that no nation can claim sovereignty over celestial bodies, but it's less clear how resources can be extracted or used. As mining and settlement become realistic possibilities, new international frameworks will be needed to ensure that space exploration benefits all of humanity, not just the wealthy or powerful. The solar system is vast, but it is finite. Earth is not the only world we can inhabit, but it is the only one currently suited to human life. Every other destination requires technology, infrastructure, and constant vigilance to survive. This makes Earth precious, a fragile oasis in the cosmic desert. As we look outward, we must also look inward, caring for the world that made us and learning the lessons of sustainability that will be essential for survival anywhere in the solar system. The coming century may see humans living and working on multiple worlds. Children born on Mars will grow up under a different sky, experiencing weaker gravity and never breathing Earth's air. They'll be Martians, shaped by their environment just as we are shaped by Earth. But they'll also be human, carrying with them the same curiosity, creativity, and drive to explore that has defined our species since we first looked up at the stars and wondered what was out there. The solar system is no longer a distant abstraction. It's becoming our neighborhood, a collection of worlds we can visit, study, and perhaps one day call home. The journey has only just begun, but each discovery, each mission, each step outward brings us closer to a future where humanity is no longer confined to a single world, but spread across the solar system, exploring, learning, and thriving among the planets. The cosmic perspective. When you look up at the night sky, you're seeing the solar system embedded in the vast canvas of the Milky Way. The planets, though they seem to wander against the fixed stars, are our immediate neighbors, bound to the sun by gravity, traveling together through space. But zoom out further, and the solar system becomes a single point, a tiny bubble of warmth in the cold interstellar medium. The sun, with all its planets, moons, and smaller bodies, occupies a region about 200,000 astronomical units across if we include the Oort cloud. Yet the nearest star system, Alpha Centauri, is over 260,000 astronomical units away. The gap between stars is vast, filled with thin gas, dust, and the occasional rogue planet ejected from its home system. We are isolated, separated from our nearest stellar neighbors by distances that would take tens of thousands of years to cross even at the fastest speeds our spacecraft can achieve. This isolation has profound implications. It means the solar system evolved in relative independence, shaped primarily by internal processes rather than external influences. Passing stars occasionally perturb the Oort cloud, sending comets into the inner solar system, but direct encounters are extremely rare. The last time a star came close enough to significantly disrupt the solar system was probably millions of years ago. Yet we are not completely isolated. The Sun orbits within the Orion Spur, a minor arm of the Milky Way galaxy, and our motion through the galaxy exposes us to varying levels of cosmic radiation. Every 30 million years or so, the solar system crosses through the galactic plane, where the density of gas and dust is slightly higher. Some scientists have speculated that these crossings might correlate with increased comet impacts or subtle changes in Earth's climate, though the evidence remains inconclusive. The solar system is also constantly bathed in cosmic rays, high-energy particles accelerated by supernovae, black holes, and other violent cosmic events. These particles stream through space at nearly the speed of light, and some penetrate Earth's atmosphere, creating showers of secondary particles that occasionally strike the ground. The solar wind provides some shielding, but during solar minimum, when the sun's magnetic activity is low, more cosmic rays reach the inner solar system. We live in a relatively quiet neighborhood of the galaxy. There are no nearby supernova remnants, no massive stars on the verge of exploding, no close encounters with black holes. This stability has persisted for billions of years, allowing life on Earth to evolve without catastrophic interruptions from cosmic events. But the galaxy is a dynamic place, and eventually, the solar system's environment will change. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. The two spiral galaxies will merge over several billion years, creating a new elliptical galaxy, sometimes called Milkomeda. Stars will be flung into new orbits, and the Sun may end up in a completely different part of the combined galaxy. But individual stars rarely collide during such mergers. Space is so vast that even during a galactic collision, the odds of any two stars hitting each other are infinitesimally small. By the time this merger occurs, the Sun will be well into its red giant phase, and Earth will either have been consumed or rendered uninhabitable. The solar system as we know it will be unrecognizable. But the story won't necessarily end there. The atoms that make up the planets and moons will persist, scattered and reformed perhaps into new worlds around younger stars. Nothing in the universe is truly destroyed, only transformed. This cosmic perspective reminds us that the solar system is temporary. It had a beginning, shaped by the collapse of a molecular cloud and the accretion of a protoplanetary disk. It will have an end when the Sun exhausts its fuel and the planets either fall into the dying star or drift away into the darkness. But for now, in this brief moment of cosmic time, the solar system is our home, a collection of worlds that has nurtured life and consciousness, a place where matter has organized itself into forms complex enough to wonder about its own origins. We are part of the solar system's story, but we are also observers of it. We send spacecraft to distant worlds, peer through telescopes at faint objects in the Kuiper Belt, and study meteorites that fell to Earth from the asteroid belt. We are learning the solar system's history, reading it in the craters on Mercury, the dry riverbeds on Mars, the icy plumes of Enceladus. Each discovery adds a new chapter to the story, deepening our understanding of where we came from and where we might be going. The solar system is not static. It is evolving, changing, responding to the slow, patient forces of gravity, radiation, and time. The planet's orbits shift slightly over millions of years. Moons spiral inward or outward due to tidal forces. Asteroids collide and fragment. Comets evaporate as they pass close to the Sun. The solar system of today is not the same as it was a billion years ago, and it will be different again a billion years in the future. But through all these changes, the fundamental laws of physics remain constant. Gravity still pulls, light still travels, energy still conserves. These laws shape the solar system, determine what is possible and what is not, and create the patterns we observe. Understanding these laws is the key to understanding the solar system, and by extension, understanding our place in the universe. We are made of the same atoms that make up the planets and stars. We are governed by the same laws of physics. We are part of the solar system, not separate from it. And as we continue to explore, we discover not just facts about distant worlds, but truths about ourselves, about origins, our potential, and our future among the stars.